Software engineering is experiencing a mechanical shift. On side, traditional coding, line by line. On the other, autonomous agents generate hundreds of lines in seconds. Right now, the dominant way developers interact with these models is through vibe coding. This interaction relies on granular, conversational prompts to steer an agent toward a completed feature. This approach optimizes for throughput, but the cost is architectural control. The agent types fast, while the developer loses sight of the underlying system design. At a small scale, you can catch the errors, but looking at this logic tree, we see a specific failure mode. When an agent hits an ambiguous requirement, it often guesses the answer to save a conversational turn, rather than halting for user input. Unchecked throughput without governance creates untraceable code and architectural drift. There is a common assumption that smarter autonomous agents or larger context windows will eventually solve these complex design failures. However, even highly capable models fail to produce maintainable software when given broad feature requests without structural constraints. This timeline illustrates the risk. Instead of pausing to confirm a database selection, the agent skips planning and generates raw SQL. Missing this checkpoint means ignoring cross-cutting concerns like security and error handling, infecting the architecture with downstream failures. These failures stem from a lack of engineering methodology that model capability alone cannot resolve. Language models operate as a new layer of computational abstraction, functioning like a stateless processor rather than the human collaborator they often resemble in chat windows. Early programming had almost no abstraction. The physical structure of the machine, like the pins on a brass cylinder, was the literal program. Assembly shifted that logic inside the CPU. By using microcode and logic gates, engineers could move information between registers without rewiring the machine. High-level languages like C raised the abstraction again, using compilers to translate readable syntax into machine instructions and decoupling logic from raw hardware. Throughout these shifts, developers maintained control by understanding the layer immediately below their tools, a practice that remains essential today. The LLM acts as a stateless CPU. It tokenizes context to produce probabilistic outputs based on the information it is currently holding. Physical programming and microcode relied on the predictability of the hardware. Because language models are probabilistic, they require an external, engineered governance layer to function as a reliable compiler of intent. Relying on a conversational chat history to maintain architectural intent is fragile. This is why we move towards spec-driven development, or SDD. SDD shifts the project's logic out of the ephemeral chat window and into durable artifacts stored on the disk. This requires a specific file architecture, a spec document for intent, a plan for strategy, tasks, and a contracts directory. The spec file is the authoritative record. Every piece of code the agent generates is routed through and validated against this document. This creates a bidirectional contract. Humans steer intent by writing the spec, and the AI steers implementation by reading it. By making the file system authoritative, we eliminate the risk of critical decisions being lost when a context window clears. Even with a durable spec, a multi-agent system can modify files at speeds that outpace human review. Agentic governance addresses this by creating a mechanical refusal layer that enforces strict development lifecycle discipline. The process is separated into hard boundaries. If an agent tries to move from planning to implementation, a mechanical gate blocks it. Advancing requires a review. One human authorization lets the agent advance exactly one boundary, ensuring no agent simulates an approval. Every verdict and drift event is written to a ledger file, creating a time-stamped audit trail of every architectural decision. Governance forces the AI to surface questions instead of auto-resolving them, keeping the developer anchored at every critical junction. When governance dictates the process, the project achieves state durability. The methodology survives even if the host model is switched. In a standard workflow, closing the IDE or filling the context window means the agent's memory of the session is erased. In a governed system, the boundary state and the iteration plan remain parked in a local state file, preserving the exact moment development stopped. This allows a developer to restart the session using an entirely different host, like Claude Code or Codex, and resume from the exact same gate without losing progress. Establishing the artifact on disk as the authoritative record enables true host agnosticism. Engineers can switch models to find the best reasoning for a specific task without losing their place in the architecture. This shift changes the engineer's daily reality. The role moves away from manual syntax generation and towards system orchestration. Developers become the thinkers and planners, ruling an ecosystem of agents that execute the manual labor. While agents optimize for task speed, the human operator remains the sole entity responsible for the security and logical soundness of the system. Speed without a human-operated dashboard for discipline creates architectural vulnerabilities that can compromise the integrity of the entire system. Hard boundaries allow enterprise engineering to scale multi-agent frameworks without the risk of code-base collapse. The methodology is the foundation. The spec is authoritative, drift is logged, and boundaries are unbreakable stops. This is how we harness the raw throughput of AI while preserving the rigorous safety and precision of traditional engineering. In an ecosystem of rapidly evolving models, the differentiator for engineering success is the rigor of the methodology rather than the raw intelligence of the model.